Wiener filter or minimum mean square error filter. So this is the most useful restoration filter. So Wiener filter. We have seen inverse filter. So in that due to the drawback, so that is practically not used one. So here this one is the Wiener filter. So very useful one. So now here the main objective is here by considering the minimum mean square error, that is nothing but E square is the expected value of f minus f kappa whole square. By considering this equation, then they developed one transfer function for the restoration filter. So that is nothing but f cap of u comma v is equal to h star of u comma v sf of u comma v by sf of u comma v mod of h of u comma v whole square plus sn of u comma v into g of u comma v. So this one is actually derived from the condition, what is that, minimum mean square error or optimized mean square error equation. So here no need to here discuss about the derivation. So here just take the formula. So under this condition, so we have established one formula. So can observe this formula. So then you can understand the Wiener filter directly, right? Now f cap of u comma v equation is modified like h star of u comma v divided by, so common the sf of u comma v in the denominator. So then you can cancel this one. So now here in the denominator h of mod of h of u comma v whole square plus ratio Sn of u comma v divided by Sf of u comma v into g of u comma v. Of course, now here h star of u comma v into h of u comma v is nothing but mod of h of u comma v whole square. That's why here product numerator denominator with the h of u comma v. So then you can get the formula like this, mod of h of u comma v whole square divided by h of u comma v into this one, total this one, into g of u comma v. Here Sn and Sf, these two are power spectrum values, PSD values. So that is nothing but a power spectrum of undegraded image is the Sf of u comma v. Power spectrum of noise is nothing but Sn of u comma v. So here also it has certain formulas based on f Sf of u comma v is developed, and based on n Sn of u comma v is developed, right? So now here all the values are here. When you observe this one, so all the functions are familiar, right? So we know that, right? We know the g of u comma v, then h of u comma v, right? So now f of u comma v, from the f of u comma v, sf of u comma v is obtained. From n of u comma v, sn of u comma v is obtained, right? So this is the equation. So now here, if you observe this equation, right? So f cap of u comma v, that means the restored image, which should be the replica of the original image, that is equal to, right? So this total equation that depends on this ratio. That depends on this ratio. What is that? Sn of u comma v by sf of u comma v. So what I said to you, Sn of u comma v came from n of u comma v. Sf of u comma v came from f of u comma v. We don't know f of u comma v here. We know only what is that? Degraded image. What is that? G of u comma v. Now estimated degraded function. What is that? H of u comma v. By using blind deconvolution methods, we can estimate h of u comma v. So we know G, we know H, and of course we know some value, n value, noise, right? From noise we can estimate, we can find out the PSD value, Sn of u comma v. But we don't know the Sf of u comma v, since we don't know the input image, f of u comma v, and that means f of x comma y. So it is difficult to estimate here, right? That's why here smartly they are taking certain ratio here. So here this one is that means one value is there, or some integer is there. So that means the ratio gives you certain integer, right? So that's why here smartly they are considering this ratio as k. K is chosen manually to obtain the best visual result. So that means here take this transfer function, right? So as a restoration filter, now by varying by putting different k values, check the output. So for what value of k, so you can get the better value, then just fixed that value, right? So as a k, right? So that is the here the very important one. So now if you observe this one, what here this one is actually here more advantages are there. So what is the drawback here? This one. So here we don't know this ratio. We should estimate. We should what is that, manually change the k value. So until you can get the best image, right? So now it's okay. Now coming to the examples, this is an original image, right? So that means if I add the particular restoration filter to the acquisition system, right? So that acquisition system provides this image. If I add the restoration filter to that particular system, if I use the inverse filter, full inverse filter, so what do you mean by full inverse filter? So that means for all UV values, so that h of u comma v is there. So that's why. So result of the full inverse filter. So see this, so much of noise is there. So if you observe this one, for d naught is equal to 70. So here if you limit the u comma v values, so you can see the betterment, right? So here the same way, take the blurred image due to turbulence, right? So if I apply the Wiener filter here, full Wiener filter here, so here this is the blurred image. My acquisition system gives this output. So but I just append the one restoration system, that is a Wiener filter, to the acquisition system. Then I can improve the image like this. See this, right? So now here observe the different one. So it's the original image. So same thing, the previous case, right? So with the d naught 70, this is the output, right? So here, so original image, I cannot get the actual original image from by using this inverse filter, right? So it is not the much good image when compared with this, right? So here if I take blurred image, so what is the result of the Wiener filter? It's a good image without knowing the input image. So actually I have only blurred image. So I just by estimating h of u comma v from atmospheric turbulence mathematical modeling. So based on that h of u comma v and based on the designing of Wiener filter, I can improve the, or I can restore the image like this, right? Now see this. So this is input. Actually here I am applying standard deviations like noise values. These are the different noises. So noise is there, and also some degraded function is there, that is due to by motion. So that means blurriness is there. So if I apply inverse filter to this, so I can't get the proper output, right? See this is an output. When I apply Wiener filter, see, so improvement is there. From this, I can improve the input image, right? So like this, right? Now coming to this one. So now here, see this and then see the results. See this. So in such a case, so that means if noise is high, fully dominates the second term here in the inverse filter. That's why I can we got the, what is that, this type of noisy images, right? If noise is low, so I can recover the image by using inverse filter also, right? So here by using Wiener filter, right? So picture clarity is improved. So here k is chosen manually, of course remember that point. So now here coming to the, what is the third filter, constrained least squares filter. What is the problem in the previous case? K value. K is nothing but ratio of noise to image. Am I correct? Noise to image power spectrum values. So we don't know, it is very difficult to estimate this value. That's why, so we have chosen K value manually. Then that is the drawback here actually. So okay, now coming to the third one, what is the constrained least squares filter? Here we just develop one constraint here. What is that? If you write the equation, this equation, degradation model equation in matrix form, G is nothing but H into F plus N. So from this, G minus HF should be equal to noise. So G minus HF mod square is nothing but mod N whole square. So this mod is nothing but actually it is represented like this. Mod W whole square is nothing but WT, W transpose W, right? Based on this. So okay, here this is the constraint here. So right, based on this constraint, to minimize the particular criterion function, so I can get the restored image, right? Good image, right? I can suppress the noise also here. I can suppress the error also here. What is the error here? F cap of x comma y difference with the f of x comma y, right? So now, so based on this criteria function, so here I developed one, what is that? Equation, transfer function, f kappa u comma v. Based on all this, we have one transfer function here. What is that? H star of u comma v by mod of h of u comma v whole square plus gamma mod of p of u comma v whole square g of u comma v, where p of u comma v is the Fourier transform of p of x comma y. This one is nothing but 3 by 3 matrix, 0 minus 1 0 minus 1 4 minus 1 0 minus 1 0. As it is, we just consider this equation. So and then no need of derivation here. Just observe this equation, constraint least square filter transfer function, and then what is the restored image, right? We will observe that one only. Okay. Now here, constraint least square filter formula is this one, right? So this one. What is gamma is here? Gamma is adaptively adjusted to achieve the best result. Here also gamma is variable. So to achieve the best result, you just vary the gamma. So okay, here this is the input. So these are the outputs coming from these three inputs, right? So observe. When I apply Wiener filter, I got the outputs like this. When I apply this constrained least square filter, so improvement is there. So see this, these are the outputs. Okay, right? See this. These are the outputs of constrained least square filter. These are the outputs of Wiener filter. Right? Okay, so here is a one algorithm also there, but here not important to BTech students, so it is available. So if you are interested, you may concentrate on this also, right? So these are some more examples here, right? So thank you.